So last time we started reductions that are randomized. So which means that we say that problem A. So we say that problem A reduces to problem B. We say that problem A reduces to problem B in randomized polynomial time if input x meant for problem A can be transformed to a string m of x, which will be a yes string of B with high probability. High should be much above half. So we have fixed it to be 2/3, but as we saw before, the probability can be amplified. So it can be anything more than inverse polynomial away from half, and that can be made inverse exponentially away from 1. And we have seen an example of this major theorem we did, that polynomial hierarchy reduces to parity P via randomized reductions, right? So we reduce sigma I sat to parity sat in a randomized way. But now we can also define smaller classes, like smaller than the polynomial hierarchy, I mean, or parity P, like BP.NP. Okay, BP.NP is the randomized version of NP. So these are the set of those problems that randomized polytime reduced to SAT. And in general, we can define BP.C for any complexity class C. We don't know whether NP is equal to BP.NP, but it is conjectured. There is some theoretical evidence for this. And if we take co, then we get randomized version of co-NP. So BP.co-NP. And same game we can play with not time restricted but space restricted classes, like log space class. Work tape is log n space, while the input tape is full, is n. So BPL, for example, is the set of those problems which can be solved by a probabilistic Turing machine that is log space restricted. And RL is the one-sided error version of this. Okay, so this is a probabilistic Turing machine log space restricted with, for yes string it says yes with probability 2/3, and no string it always rejects, it cannot say yes. Okay, so RL is one-sided while BPL is two-sided error. And what you can show immediately is that log space is in RL, right, because that has no random bits. RL is in BPL. So remember that RL can also be defined via probability half, right? It doesn't matter. We can put it here. And then you can amplify it to 2/3, and that then is of course contained in BPL. And BPL is contained in P. Okay, this is the non-trivial part. So this I leave as an exercise. Why is BPL contained in P? So here the idea is that in log space it can only use log many random bits. So you can actually go over all of them, and you can compute the probability for an input string x in polynomial time. Okay, so if the probability is more than 2/3, then more than R are accepting, more than 2/3 of the R's are accepting, then you say it's a yes string. If only 1/3 were accepting, then you say it's a no string. So this simulation can be done in polynomial time. Other examples are undirected connectivity. Okay, so UCon is given a graph and two vertices S to T, whether there is a path, and for which you know a polynomial time algorithm, right, DFS. So believe it or not, this can also be done in log space if you have random bits. So this has a simple RL algorithm. So the idea is that you pick random neighbors and do a random walk. Okay, so in the graph starting from S, if you do a random walk, uh, it's a great exercise to show that if T is in the same connected component, then with high probability you will reach T. Okay, so which means that, and the random walk can be done in log space, because when you are at a vertex V, then you only need to pick a neighbor, and that only needs login bits, random bits. And second example is graph isomorphism. So graph isomorphism is this problem of GI where you are given two graphs. You can assume directed weighted graphs, general graphs, whether the two are isomorphic. So this is in BP.NP. Okay, that was a major result several decades ago. It's a surprising thing that graph isomorphism. So if there is an isomorphism, then you can verify it if somebody gives it to you. So it's already in NP. But if there is no isomorphism, what do? It seems that you have to go over all the permutations. That's n factorial, right? But here we are claiming that actually it can be done almost in copy, and in randomized version of NP, co-NP. So GI is kind of an NP intersection co-NP. Okay, so you can think of this as randomized version of NP intersection co-NP. So GI is then not very difficult. It's not very high up in the polynomial hierarchy. It's actually lower than NP, right? This is what this result is kind of saying. And in a major breakthrough, Babaish gave actually an algorithm in 2015. Okay, so not many years ago, Babaish showed that graph isomorphism is in quasi P. So what is quasi P? This is slightly above polynomial time. It's the time complexity is something like 2 raised to log n to the C. Okay, so instead of 2 raised to n, which will be exponential, and 2 raised to log n, which will be polynomial time, this is somewhere in between, but closer to polynomial time. It's 2 raised to, think of log square n, right? So that's n to the log n. So exponent is not a constant, but at the same time it's also very slowly growing. Okay, so graph isomorphism has now a sub-exponential algorithm, in fact quasi polynomial algorithm, but we still don't know whether it is in P, and now we will show that it's in this randomized version of NP intersection co-NP. So let's do that. So what is the language GI? That is easy to define. its pair of graphs finite graphs G1, G2 and they are isomorphic. Right. So, isomorphic, remember, means that there is a way to relabel G2 so that it becomes equal to G1. So, it is just a relabeling of the vertices. And graph non-isomorphism is the opposite. It is the set of pairs of graphs such that they are not isomorphic. Right. So, isomorphic pairs versus non-isomorphic pairs. And what you can show immediately, as I mentioned before, is that graph isomorphism is in NP because there is a permutation making G1, G2 equal. So, somebody gives you that permutation, you can easily check. So, it is easy to verify. And graph non-isomorphism hence is in KANPUR-NP, right, because it is just the complement problem. But what is open, it is still open, is whether both these problems are in the intersection in both these classes. So, whether graph isomorphism is in KANPUR, graph non-isomorphism is in NP, and of course, if graph isomorphism is in P. Okay, so all these questions, the first two are equivalent and the third is asking for a practical algorithm for graph isomorphism, and that we do not know, we actually do not even know probabilistic algorithms. Okay, so, we do not even know whether graph isomorphism is in BPP. That is a major open question. So, what we will do now is focus on GI. Okay, so, we will put graph non-isomorphism in BP.NP. So, that is randomized version of NP, which kind of makes the definition that we started with BP.NP very useful, right. That was the purpose, that we will actually show a problem here, an interesting problem which we do not know any lower, and that is graph non-isomorphism. This is also called, this is also an example of what is called a one round Merlin-Arthur interactive protocol. Merlin is the all powerful king, or Merlin is the all powerful advisor, prover, and Arthur is a weaker king. Okay, so, Merlin sends proofs to Arthur, and Arthur is a polynomial time verifier, in fact a randomized polynomial time verifier, and he has to verify without knowing the without knowing everything. Okay. So, Arthur is much weaker than Merlin. So, there are these definitions in complexity theory which we do in advanced courses. Here we will not do it, we will just do GNI proof, and that is a strong motivation for these interactive protocols with public coins. So, each of these terms actually define complexity classes. Okay, one round, how many rounds, then Merlin Arthur based interactive protocols. So let's do this formally. So Goldwasser, Sipser showed this theorem and started this big area of interactive protocols in complexity theory. So GNI they showed is in BP.NP. So what is the idea? So the idea is that when graphs are non-isomorphic, this G1, G2, there are many graphs which are isomorphic to one of them. In comparison to when they are isomorphic, G1, G2 are isomorphic, then only half that number of graphs are isomorphic to either one of these two. So there is a gap. Okay, you have more graphs that are isomorphic if G1, G2 are not, and you have less graphs that are isomorphic if G1, G2 are. So let's use that. So the number of graphs each such that each is isomorphic to G1 or G2 okay, so one of these each is isomorphic to one of them. This is more and in fact doubly more when G1, G2 are different, non-isomorphic than when they are. Okay. So can we utilize this gap to give a certificate, small certificate that they are not isomorphic? So this largeness can be detected in NP. So that's what BP.NP is good for. It will be able to detect that the number of H is more, and hence G1, G2 are non-isomorphic. So yeah, you can see that we are somehow reducing non-isomorphism question to isomorphism once, right? Because we are talking about now each isomorphic to G1. So in a way, we are reducing it to the opposite. We reduce non-isomorphism to isomorphism. Okay, and since isomorphism is in NP, we get this NP result. So that's the plan. Let's implement it. So formally, consider the set S associated with on n vertices so we can assume that G1, G2 have the same vertex set and the same will be for H. So S is the set of H. So this is an important definition. We have H, but we also keep a permutation pi with that. So graph H has vertices n H is isomorphic to G1 or it is isomorphic to G2. And what is pi? Pi is an automorphism of H. So this we are keeping for a technical reason. The reason being that we will need a bound, or in fact we will need the size of S exactly. So keeping the automorphism helps us in that. Let's see how. So if G1 and G2 are isomorphic, then the number of H pi is pairs is H such that H is isomorphic to G1. I mean, if H is isomorphic to G1, it's also isomorphic to G2, and there is no other H possible. That's the number of H, and what is the number of pi's? So that is the number of automorphisms. Right? Note that number of automorphisms of H and G1 will be the same. So for every H, we are multiplying by number of automorphisms of G1. That actually simplifies our calculation for S, because so how many graphs are isomorphic to G1? That is so number of permutations, and out of these you have to divide by how many permutations are giving you the same graph H. So that's number of automorphisms of H. And then you are multiplying by number of automorphisms of G1. So you get n factorial. Okay, you can think about this if it's not clear. It's basically a count on how many H are isomorphic to G1. That's what you need to understand. And so size of S becomes this number that we already know, it's n factorial. On the other hand, if the graphs are non-isomorphic, then what happens is size of S is the case when H is isomorphic to G1 versus G2. So number of H pi such that H is isomorphic to G1. The GI. Okay, so the sets, the part of S corresponding to G1 and the part of S corresponding to G2, you are summing them up. Each of them you know is n factorial, so you get 2 times n factorial. Right. Note that these two sets are disjoint. Right. There is no H that is present in both, because that would mean that H is isomorphic to both G1 and G2, but G1, G2 are non-isomorphic, so that cannot happen. So hence we are just adding these two numbers. So again, in the first case, isomorphism, isomorphic case you have n factorial, and non-isomorphic case you have 2 n factorial. So that is the gap which I alluded to in the idea. So S is doubly large when G1 G2 is a yes instance of GNI. And we know the size. So that's an important thing, knowing the size or at least size bounds, and we'll use this now in the protocol. So now we give a general method to test this size difference. In BP.NP. So we use hash functions. Okay, so here you can recall the pH to parity P reduction. Because the properties of hash functions that we prove there, we'll be using them. So let H be the map from this M bit vector to K bit vector. It basically sends U to matrix multiplication, right? So BU plus small b. Where B is so suitable dimension, appropriate dimensions. It's K cross M, and small b is K bit vector. So you notice that BU is K cross M times M cross 1. So you get K cross 1, which is small b dimension. So you can add. Okay, so using matrices, you can make basically random matrices define random hash functions. And the idea is that a big M you are compressing down to K. Fine. So, and we also, yeah, so basically this is useful when right. So hashing is used to almost always the effect is to actually compress the input. So M bits it will reduce to K bits with certain properties. So we'll let us now recall those properties. So the probability that there is an element X in the set S which is in the pre-image of 0. As you randomly pick the matrices, so this probability is at least size of S by 2 raised to K, right? There are S elements in the set S, size of S many elements, and there are 2 raised to k points in the image, an x that is mapping to from S to 0. So that probability is S by 2 raised to k, slightly less than that. And this probability is at most S by 2 raised to k. Okay, so these are the properties that we had shown. What is the chance that an element in S maps to 0? This single point in the image. Upper bound, this is upper bounded by S by 2 raised to k. I mean, roughly hitting one point in the image, fixed point probability is 1 by 2 raised to k, and there are S elements, so it cannot be more than S by 2 raised to k. But then what may happen is collisions. So many elements may be mapping to the same element in the image. So for that, the probability may fall, but it may not fall by more than S choose 2 by 2 raised to 2k. That's the rough intuition for these two properties. Let us now use it on our S and see the difference. When S is small, what happens? When S is large, what happens? So we have size of S n factorial or 2 times n factorial. So let's fix k such that 2 raised to k minus 2 and 2 raised to k minus 1 sandwich n 2n factorial. Okay, so basically k is like log of size of S, upper bound on size of S. Let's fix k to be that. So the image of the hash function, this 2 raised to k, it is slightly more, it is actually doubly more than upper bound for S. Okay, so we are mapping S to a slightly bigger domain, but k is this. So now if the set is of size n factorial, then the probability above, right, that probability is less than equal to S by, which is S by 2 raised to k, becomes n factorial by 2 raised to k. Let's call this p. Okay, so that's the upper bound on the probability. And when S is 2n factorial, then the probability is greater than equal to S by 2 raised to k minus S choose 2 by 2 raised to 2k, which is at least, so let's take S by 2 raised to k out. We have 1 minus S by, so this is just simple calculation. So S choose 2 is S times S minus 1. We approximate it by S square by 2, and you get this, which is greater than equal to okay, so let's do this later.